Hello, and in today's video, we are going to be going over solutions to Algebra 2's Unit 2B test review. So let's jump right in. Get your pens and pencils ready, a piece of paper, maybe a calculator, and remember, at any point in this video, you can pause, rewind, and do whatever you need to do to make sure that you get all of the information that you need to be best prepared for the Unit 2B exam. So let's get started. The very first question on the Unit 2B review is to simplify this equation. So I numbered this number 1. And the question says to simplify the following equation. 5x minus 15 all over 5. Now, remember, when we ask to simplify, we're really just trying to make sure that any common factors from the numerator and denominator cancel out, and I end up with an expression that is more simple than the one that we've started with. That's the whole objective here. So really, the main point of simplifying is to factor out either greatest common factors, factor an expression, what have you, in the hopes that eventually something will cancel out. So here, as I'm looking at my expression, my denominator is just the number 5. I know that my denominator cannot be simplified any further than just a number. So I'm really going to be focusing on my numerator. And for this example, 5x minus 15, I notice that there's a greatest common factor between 5x and 15. There's a GCF between 5x and 15. I notice that 5 actually divides, obviously, 5x, and 5 divides 15. So that's my greatest common factor. My GCF is the number 5. And when I factor the 5 out, what's left behind is x, because 5 times x is 5x, and negative 3, because 5 times negative 3 is negative 15, all over 5. Now here we notice that we finally have something in the numerator that is exactly the same in the denominator. In this case, it's the number 5. So those cancel, leaving our final expression as x minus 3. And that is much simpler than 5x minus 15 over 5, so I know I have simplified fully. Sometimes you will have an expression like this. Sometimes you might still end up with a rational expression, just a little bit more simple. Sometimes you can simplify all the way down to a single value, a single number like 5. But in this instance, the furthest we can simplify is down to x minus 3. Now looking at the second equation on this Unit 2B review, it says, number 2 says, what is an equivalent equation for the following equation? So it's asking us, what is an equivalent equation for the following equation? And it gives our following equation as x squared minus 3x minus 4 all over 4x plus 4. So it says, what is an equivalent equation for the following equation? Now, something I want to draw your guys' attention to that is a subtlety that one might miss is the word equivalent. And equivalent means equal. What is equal? to this equation. So what's a different way to write this equation? Equation for equation, right? So I want to know, really, and whenever I'm asking if something's equivalent, it means it's exactly the same thing. It is equal to it. And this question is nice coming after the simplify, because to find an equivalent equation, we do some sort of algebraic manipulation to figure out that something's actually equal to another expression. So, for example, looking at this rational expression, x squared minus 3x minus 4 divided by 4x plus 4. I noticed that what we've been doing with these, the usual situation is we have been factoring both the numerator and the denominator and seeing what we get, right? So an equivalent statement, something that is exactly the same as the other, is maybe factoring the numerator and factoring the denominator. Now, my numerator, let's just focus on the numerator, okay? My numerator is factorable, right? If I kind of covered it up, oopsie, if I covered it up, which sometimes I like to just grab a piece of paper and just cover it up, I would ask myself what multiplies to 4 but adds to -3. And those factors, what multiplies to -4 but adds up to -3, are going to be 4 times 1, right? Because 4 times 1 is 4. But we need it to be negative, so one of them has to be negative. And then the only way that I can get -3 is if 4 is negative. So -4 plus 1, if I added them together, that gives me -3, and that's my middle term. So that's how I know that my factors should be x minus 4 and x plus 1. So this expression is equal to x squared minus 3x minus 4. And here's how I can check. If you're ever struggling with, if you're not sure if your factors are true, you can actually perform this polynomial multiplication. X times x, right? X times x is x squared. X times positive 1 is positive x. -4 times x is minus 4x. -4 times 1 is -4. Combining these like terms, I get x squared minus 3x minus 4, which is exactly the expression I was trying to factor. So that's what I mean by equivalent. These are equal. This expression is exactly the same as this expression. But that was just the numerator. That was just the numerator. Now we have to focus on our denominator. And it is a binomial, 2 terms, and it's a linear binomial, meaning that the degree is 1, right? 4x plus 4. So I'm not going to factor it quite like this. I'm going to look and see if there's a greatest common factor between the two. So 4x plus 4, they both have 4 in common, so 4 is my greatest common factor. If I factor out 4, what's left behind is x plus 1, because 4 times x is 4x, and 4 times 1 is 4. Now, right now I have this expression is exactly equal to this expression, right? So far they are equivalent. But what we've been doing with factored expressions, like problem number 1, is we have been simplifying it. They are the same, right? So now I'm looking for factors on the top that are exactly the same as factors on the bottom. X plus 1 and x plus 1 cancel. So again, the same expression is equal to x minus 4 over 4. That is the most simplified expression that I have. X minus 4 divided by 4 is equal to this factorization where these common factors cancel out, which is also equal to our original equation. So when we're talking about finding something that's equivalent, Basically, we are rewriting the expression in any way that we can, performing some sort of algebraic manipulation, and simplifying. Let's see what question number 3 has in store for us. Question number 3 says, polynomial division and actually rational expressions division. Number 3 says to divide. And it wants us to divide x squared minus 6x plus 9 all over x divided by x minus 3 over x squared. And when we have rational expression division, a rational expression divided by a rational expression, what this calls for is a very specific technique. And for my class, I always tell students to factor first and then keep, change, flip. When you're dividing, I always ask us to factor everything first, then keep, change, flip so we don't forget to factor. That's my really only reasoning behind that. You can keep, change, flip first and then factor, but for me personally, I like to factor everything first, every expression, make sure every expression is fully factored, and then keep, change, flip, and simplify. So I'm going to do that first. I'm going to factor everything first. And I notice as I'm kind of going from left to right, as we do, left to right, even covering up the denominator, x squared minus 6x plus 9 can be factored, right? I need factors of 9 that add up to 6. And that is going to be the values of 9 that add up to 6. 3 times 3, right? 3 times 3 is 9. But I need negative 6, so I can make them both negative because negative 3 times negative 3 is positive 9, and negative 3 plus negative 3 is negative 6. So I factored the top expression. The denominator is just x, so he is luckily fully factored. Then we have divided by x minus 3 is a linear term. Notice that this is also a linear term, so I'm just going to leave them alone. X minus 3 is good, and at this time, x squared, we have no reason to want to change that. So we have factored the entire expressions first. Now we get to keep, change, flip, because in order to divide, this is called complex fractions, a fraction divided by a fraction, or a rational expression divided by a rational expression, we want to keep the first expression, change the operation from division to multiplication, and flip the second expression, or multiply essentially by the reciprocal. So keep this first expression exactly as is. Do not change it in any way. So that means we have x minus 3 times x minus 3 all over x. Didn't do a darn thing. But we are going to change this operation from division to multiplication. And lastly, we are going to flip our final rational expression. What's on the denominator goes to the numerator. What's on the numerator goes to the denominator. So x squared is on the top, and x minus 3 is on the bottom. Now we're at a multiplication problem. We multiply the numerators directly across, multiply the denominators directly across. And when we do so, we are looking for exact factors that match exactly, that are able to be canceled out. So for example, x minus 3 and x minus 3 are able to be canceled out. So if I multiply the numerator straight across, I have x minus 3 times x squared all over x right now. But we have a hidden piece of information that can be canceled. okay? A hidden piece of information that can be canceled. And let me show you why. Okay, so x squared can be divided by x. And here's the reason why. Since we're talking about equivalencies, right? And notice we have equal signs here. X minus 3 times x squared could be x times x, right? All over x. And these expressions are being multiplied. X times x is x squared. So I just rewrote x squared as x times x. X minus 3 stayed the same, and the denominator has x. Notice now I have an exact common factor again that I can cancel out. So it was a little tricky here with this x squared. At first, I had no reason to suspect that I needed to break up the x squared. It wasn't until the very end that I realized I have another opportunity to simplify further. So my final answer for this polynomial division, I'm sorry, I keep calling polynomial division. It is rational expression division. X squared minus 6x plus 9 divided by x, divided by another rational expression, x minus 3 over x squared, is equal to x minus 3 times x. Or you could rewrite it as x times x minus 3. The order does not matter, because we know 1 times 2 is the same as 2 times 1. Cool. So let's talk about question number 4. Okay, question number 4 wants us to add rational expressions together. So I'm going to erase everything on this whiteboard and rewrite the addition problem. So if you need to pause the video, take a little break, take a note, make sure you have everything written down, please feel free to do so at this time. So we are on problem number 4 of the Algebra 2 Unit 2B test review. So question number 4 is going to be addition. Addition, okay? So it wants us to add 5 over x minus 2 plus x minus 3 over x plus 3. And in order to add or subtract rational exponents, we must have one thing in common before we're able to add anything or subtract. Multiplying and dividing isn't that bad. When we division is just a multiplication problem, then we just multiply the numerators across and multiply the denominators across. But in addition and subtraction, we cannot just add the numerators and add the denominators. Remember, a little fact about addition or subtraction, something that's like a good to know. I'm going to write on my little sticky note here. An important fact to know is that when you add or subtract rational expressions, we must have a common denominator. Have a common denominator first. So if you don't have that written down somewhere in your notes, that is a huge fact about rational expressions. In order to add or subtract them, you must have a common denominator first. Multiplying and dividing, we don't really have to do anything to the expressions, but adding or subtracting, and heck, even solving, we must have a common denominator for our rational expressions. So the quickest, easiest way to get a common denominator is to look at the denominators we have, x minus 2 and x plus 3. Since they're linear, meaning like this looks like a line and so does this one, we're just going to multiply each one by the opposite ones. So to get our common denominator, so our first step here is going to be to get a common denominator, okay? So I'm still going to have 5 over x minus 2 but I'm going to multiply this entire expression by the opposite denominator, x plus 3 over x plus 3. Now, I multiply by this expression divided by itself because anything divided by itself is technically 1. So I'm technically not changing the problem. I'm just very clever. And we still have x minus 3 over x plus 3. But now for the second expression, we're going to multiply by the opposite denominator, x minus 2, on the top and bottom. And this was my little pro tip to my class. Remember, to make sure we have a common denominator, we check that all expressions have both, right? X minus 2, x plus 3. X plus 3, x minus 2. Check, 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 check. Once I can visually see that every expression has all of the common denominators, we are good to go. We are good to go. So now, we must have a common denominator first, comparing apples to apples. So now we actually get to do a little bit of math. So we're going to take our numerators and simplify them and keep them over our common denominators. So 5 times, actually I'm going to do this all together. Okay, 5 times x is 5x, and 5 times positive 3 is positive 15. That's our first expression. Then we have plus our second expression, x minus 3 times x minus 2, so we're going to have to do a double distribution. X times x is x squared, x times negative 2 is negative 2x, negative 3 times x is negative 3x, negative 3 times negative 2 is positive 6. And all of this entire expression, since we had common denominator here and a common denominator here, we have x plus 3 times x minus 2 as our denominator. So once we get a common denominator, we simplify the numerator. And the note is to keep the denominator factored. You don't want to undo the factoring here. Okay, and since we're in the process of simplifying the numerator, I want to combine my like terms as my next step of simplifying. Okay, I want to combine my like terms, meaning x squareds with x squareds, x's with x's, numbers with numbers. So standard form says identify the highest degree. The highest degree here is x squared. So x squared, I'm just going to write by itself in the front. Then I'm going to combine my x terms, 5x minus 2x minus 3x. So 5x minus 2x is 3x. And then subtracting 3 more x's is no x's. So I have plus 0x, or I usually just don't write anything at all. Then we got to compare our numbers. So 15 plus 6, 15 plus 6 is 16, 17, 18, 19, 20, 21. What do you know? It's 21. Awesome. All over our denominator, right? X plus 3 times x minus 2. And I can't go further. This is not a difference of squares. There's nothing to factor. Nothing is going to cancel. So for my final answer, I would say that 5 over x minus 2 plus x minus 3 over x plus 3 is equal to x squared plus 21 over x plus 3 times x plus 2. Question number 5 is similar to addition because we're going to subtract, okay? So question number 5, go ahead and get this if you need it. Pause the video right now. And question number 5 asks us to subtract the following expressions. And remember, for addition or subtraction, we follow these same rules. So I'm going to kind of leave these to the side here. We are going to subtract the following expression, 3 over x plus 2 minus 5 over x plus 4. And remember, from our sticky note, to add or subtract rational expressions, here, let me bring it here. Add or subtract rational expressions, we must have a common denominator first. Keep that here. So we got to get a common denominator, and we're going to get it in the same way that we did last time. So 3 over x plus 2, we're going to multiply by the opposite denominator on the top and bottom, times x plus 4 over x plus 4. Now this case has a subtraction, minus 5 over x plus 4. And we are going to multiply this by the opposite denominator, x plus 2 over x plus 2, right? The opposite denominator of each other. Now let's check. Do we have a common denominator in each piece? X plus 2, x plus 4, x plus 2, x plus 4. Check, 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 check. We have gotten our common denominator. Now the next step is to simplify our numerator and keep the denominator factored. So we are going to perform some multiplication in the numerator. 3 times x is 3x. 3 times 4, positive 4, is positive 12. Here's the trick, though. With subtraction, we're going to take it with this negative 5. We're going to take it with the 5. So negative 5 times x is negative 5x. That's new. And negative 5 times 2 is negative 10. We kind of did that last time. It's just I didn't bring it up. It was a subtlety that I did not bring up. And then we keep our denominator factored. X plus 2, do not expand it out, times x plus 4. You're just making way more work for yourself if you do not keep your denominator factored. And of course, we're going to combine our like terms, so x's with x's, numbers with numbers. 3x minus 5x, so 3 minus 5 is negative 2, and there were x's. And then 12, positive 12 minus 10 is positive 2, all over our common denominator of x plus 2 and x plus 4. Now, whenever you get to this step, remember, you want to see if your numerator can be factored and things can cancel, and our denominator can be factored and things can cancel. Well, our denominator is already factored. So let's see what this is equivalent to. Right? We already have x plus 2 in the numerator and x plus 4 in the denominator. So our numerator has a greatest common factor of 2. So I could pull out like maybe negative 2. I would get x minus 1, because negative 2 times x is negative 2x. Negative 2 times negative 1 is positive 2. And I noticed that this did not help me. This did not help me, right? There are no exact factors that are going to cancel out here. So my final result then would be this expression, negative 2x plus 2 over x plus 2 times x plus 4. So when you get to this step in any simplification process, whether you're adding, subtracting, multiplying, dividing, simplifying, you always want to check if the factorization helps you. There's no way to tell if the factorization will help you until you actually factor it. If it factors and something cancels out, like say this was an x plus 4, if it was an x plus 4, right? It's not, but if it was, then I could cancel terms and my final simplification would be negative 2 over x plus 2. Then that's helpful. But if it does not reduce, then I leave it as the step before. Leave it as unfactored for the numerator. So let's see problem number 6. Now we're going to move into solving rational expression equations. Solving rational equations. So go ahead and pause, get this if you need it. And we're moving up, moving on up to the other side. I think that's how that song goes. Don't come for me if that's not how it goes. So now we want to solve the following expressions. 2 over x plus 3 is equal to 6 over x minus 3. And if you guys remember, when we were solving rational expression equations, when we were solving them, we had this sticky note in our lesson, okay? Solving rational equations. Step 1, state the domain restrictions. We had to figure out where the denominators are equal to 0. Step 2, get a common denominator. We still need a common denominator. Step 3, use the numerators to write an equation. Step 4, check for extraneous solutions. When we're solving, we must follow this 4-step process, okay? So if you don't have this written down somewhere, or maybe it's lost in your notes, go ahead, pause the video, take a second to write it down. First, we have to find out where our denominators could equal to 0 because we don't divide by 0. Okay, people? We don't perform mathematical sins. We do not divide by 0. So I'm going to write over here our domain restrictions, DR for short. Okay, we set the denominators equal to 0 and we get x equals negative 3 for this first denominator. And x minus 3 equal to 0 gives us x is equal to positive 3. So we are not allowed to let x equal negative 3 or positive 3 because we would be dividing by 0. And now at this point, since we're reviewing, we know that at these values, we either have a vertical asymptote or we have a hole. So that's why our domain is restricted, because we're actually undefined at those points. So step 1, done. Step 2, get a common denominator. So it's going to be the same as the last 2 problems. Multiply by the opposite denominators. So we're going to have 2 over x plus 3. We're going to multiply by the opposite denominator on top and bottom, which is x minus 3. Okay, so x minus 3 over x minus 3. This is still equal to 6 over x minus 3 times now the opposite denominator is x plus 3 over x plus 3, because that's technically multiplying by 1. Okay, do we have a common denominator? X plus 3, x minus 3, x plus 3, x minus 3. Check, 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 check. Perfect. Step 2 is accomplished. Get a common denominator. Step 3, use the numerators to write an equation. So I usually just write just the numerators, exactly as the numerators look. X minus 3, so 2 times x minus 3 is equal to 6 times x plus 3. So I usually zoom right into my numerators for step 3. Zoom in on my numerators. I write it exactly as is, then simplify my numerator equation. So 2 times x is 2x. 2 times negative 3 is negative 6 is equal to 6 times x is 6x. 6 times 3 is 18. Now, some of you have learned a shortcut in Miss Perez's class and maybe even Mrs. Ingram's class. But for me, for my class, this is the long process and then you still get the same answer. I'll show you the shortcut in just a sec. we would solve this for x, because remember it says to solve, and solving means to solve for a specific value of x. So in my case, I'm just going to subtract 2x from both sides. Now I have -6 is equal to 4x plus 18. Subtract 18 from both sides. I get -24 is equal to 4x. To get x alone, I would divide both sides by 4. And I get x is equal to -6. So that's the long 4-step process for me. That works each and every single time. No matter how you're solving a rational expression, whether it's something equal to something, if you have addition or subtraction in there, we always follow this 4-step situation. Now, there is a shortcut only if it's something equal to something. Only for this type of situation. If you have addition or subtraction on either side of the equal sign, the shortcut does not work. But here's the shortcut, okay? I'm going to do it in this little space right here. So here's, oh, and I didn't check for my extraneous. Here's the shortcut. And this only works when you have a rational expression equal to a rational expression. Okay, that's the only time you can do this. And look, we have a rational expression equal to a rational expression. This is where we can do 2 over x plus 3 is equal to 6 over x minus 3. This is where we could do this cross multiplication. So I could say 2 times x minus 3 is equal to 6 times x plus 3. You do that cross multiplication because you'll notice this is this step right here. This is this step right here. So my solving is just step 2, after getting a common denominator using the numerators. So you end up in the same spot, just a little bit faster. You get 2x minus 6 equals 6x plus 18. Look, that's exactly the same equation that we had here. Say you didn't want to subtract 2x, say you wanted to subtract 6x, we could solve it a different way. We would get -4x minus 6 equals 18. Add 6 to both sides, you would get -4x equals positive 24. Divide by -4. You would get x equals -6 still. So either way you do it, you still get the same result, even if you solve it a little bit differently. Okay, and this shortcut can only be used when a rational expression is equal to a rational expression. But with solving, we still have to check for extraneous solutions. And you'll know that it is a solution is extraneous if it's our domain restriction value. So since -6 is not -3 and -6 is not +3, this is our solution. That is me checking for my extraneous solution. If you plugged it in, you will find that you have the same expression on the left as you have on the right. So you may use this shortcut only if you have a rational expression equal to a rational expression. I encourage you to just use the 4-step process. It still gets you there, and you make sure that you have your domain restrictions. You make sure that you get a common denominator, which is really what we have to do. And yeah, so let's do problem number 7. So the solution to this problem, when you're solving, you want a specific x value. X was equal to -6. Problem number 7 is kind of a conceptual question. It says, is the point 0,1/4 a solution for the equation y equals 1 over x plus 4. Explain or show your reasoning. So, a solution gives us a true statement at the end. Something is a solution if we plug it in and we get a true statement out. So that would be a little note that you might want to write to yourself. A solution is when you get a true statement when a value is plugged in. So in the last example, our extraneous, we would have to check that x equals -6 when we plug it in. Usually, to check that it's not extraneous, we'd plug it in and see that we get a true statement. Something does equal something else. In this instance, we have y equals 1 over x plus 4. So to see if this point is a solution for the equation, we're going to plug it in. Because remember, points come in x comma y format, right? So for this particular point, for the point 0, 1/4, here we can see that x is equal to 0 and y is equal to 1/4 because they're in those same spots. So to check if x equals 0 and y is 1/4 is a solution to this equation, we are going to plug in these values into the given equation. So we have the equation y equals 1 over x plus 4. I should probably do that in a different color, actually. So we have the equation y equals 1 over x plus 4. And if I plug in x equals 0, and y equals 1/4, I'm seeing if I get a true statement here. Is 1/4 equal to 1 over 0 plus 4? And if I simplify this expression, right, I have the right-hand side, 0 plus 4 is just 4. So you can see that I do get a true if statement, right? 1/4 does, in fact, equal 1/4, right? 1/4 is equal to 1/4. So my answer to this question, since I got a true statement when I plugged something in, I would say yes, 0, 1/4 is a solution for y equals 1 over x plus 4. So that would be something we would solve for. If I got an untrue statement, such as 1/4 is equal to 1/5, right? If it was not a true statement, then my answer would be no, it is not a solution. But since it is a true statement, yes, it is a solution. Question number 8 is asking us about the domain and range of a function. So go ahead and pause the video if you need to and get this information down, or perhaps rewatch if you need to. Question number 8 for this review for the Unit 2B test says, what is the domain and range for y is equal to 1 over x minus 3? So in order to find our domain and our range, oops, let me move this down. What is the domain and range for this rational expression? And the things that interrupt domain and range for us are horizontal asymptotes, vertical asymptotes, and holes. Those are what interrupts our domain and range. So normally our domain and range is everything, all real numbers from negative infinity to positive infinity. But the breaks in the graph mess up our domain and they mess up our range. So we need to find out where those things are. So here is a good to know for your domain, because domain is all possible x values. Our domain for rational expressions will always be all real numbers except our vertical asymptotes and except our x coordinates of the holes. And our range will be all real numbers, all possible y values except horizontal asymptotes and y coordinates of holes. So in order to figure out what the domain and range is, we need to find out where our asymptotes are and if we have any holes. So I'm going to set this to the side here. And what we need to do for this problem is first we need to identify our horizontal asymptote, vertical asymptote, and holes. Then we can write out our domain and range. Okay, so we have to figure out where the breaks in our graph is. And our breaks in our graphs are horizontal asymptotes, vertical asymptotes, and holes. So for this expression, to find our horizontal asymptotes, we need our expression in standard form, which it is, and we're going to compare the degrees using the rules. So here's another good to know, okay? To find horizontal asymptotes, we need it to be in standard form. We have to compare the degrees using the rules. And we get an equation y equals. To find the vertical asymptotes, we have to be in factored form, set the reduced denominator equal to 0, and solve for x, and we get an equation x equals. And to find holes, we set the common factors that cancel out equal to 0, also in factored form. So I kind of keep these handy to the side. And in case you were wondering what the horizontal asymptote rules are, is we're comparing the numerator to the denominator, the degrees, in standard form. And we're going to call the numerator m, the denominator degree n. Notice I have ax to the m over bx to the n. And if m is less than n, y equals 0. If m is greater than n, we don't have an asymptote. And if m is equal to n, we divide by the leading coefficients. So you might want to have these horizontal asymptote rules somewhere in your notes as well. If you don't have it, pause this video and write this down. All right, so to find my horizontal asymptote, right, I must compare my degrees. So notice I have y equals 1 over x, right? This is x to the 0th power. This is x to the 1st power. So since 0 is less than 1 or m is less than n, right? 0, degree 0 is smaller than degree 1. Looking at my rules, m is less than n. I have y equals 0 as my horizontal asymptote. That's how I use my rules. For my vertical asymptote, I set the denominator equal to 0 as long as there's no factors to cancel out. There's nothing to cancel here. There's nothing to simplify. So I set x minus 3 equal to 0 and solve for x. I get x equals 3 is my vertical asymptote. And I kind of like to do this to remind myself, like horizontal is a dashed line like this, vertical is the dashed line like this. And now holes would be if any common factors are there, if they're equal to 0. So since there are no common factors, there are no holes. Okay? So remember, our domain is all real numbers, everything except vertical asymptotes and x-coordinates of holes. So if I was to describe my domain and my range, my domain then would be all real numbers and remember domain is x values except x is equal to 3. So the shorthand of writing this would be all real numbers x cannot equal 3. That's the same thing as saying all real numbers except x equals 3. Okay, and if I were to write this in interval notation, negative infinity to 3, union 3 to positive infinity, all of these parentheses are open. Now my range, right, is all possible y values, which is why I know I have to exclude my horizontal asymptote because it's a y value, right? So my range is going to be all real numbers except where my break in my graph is at my horizontal asymptote, except y is equal to 0. And the shorthand again of that would be this bold-faced R, except y cannot equal 0 because we have an asymptote there. And my interval notation would be negative infinity to 0, not including it. And then my graph starts again from 0 to positive infinity. So either of these is acceptable. I suggest just the all real numbers except x value, all real numbers except y value. And remember, normally our domain is everything except vertical asymptotes and x-coordinate of our holes. Here we don't have any holes, so there's nothing to exclude. The range normally is all y values except the horizontal asymptote and the y-coordinate of the holes. Since we have no holes, right, as a point x comma y, there's nothing else to exclude from our domain and our range. So right now I'm going to stop the video. I'm at 53 minutes basically, and I can only record for 60-minute intervals at a time. So this is part 1. Part 2 will cover questions 9 through 11, I think it is. So I hope to see you in part 2 of the Algebra 2 Unit 2B test review.